Welcome everybody to my DConf Online 2022 talk, Mirror Mirror on the Wall, which language has the best introspection of all? Obviously the answer is D, otherwise you might be in the wrong conference. This is how I started at the D community actually in 2014 at DConf. I was talking about introspection then, and I have come full circle in a way, so we're going to talk about reflection. So what is reflection to begin with? It's the ability to inspect codes, to look into the code and see what it contains, what makes up the code base. For instance, if I look into a module, what functions and types are in that particular module? And if I drill in further, what parameters does this particular function in that module take? If we look at the types, then they could have member functions as well. What's the return type? What are the names of the arguments? That kind of thing. So it's a question of looking at what the code is. Now, what can we use reflection for? And this is really why I started the DConf 2014 to talk about this, because it wasn't clear to me what we could do with it, even though people kept saying it was powerful. And the first example everybody comes up with is serialization, which is boring, but it works. I also put pretty printers in here, but basically it's just a different kind of serialization. Interface into other languages, for instance, I've written a lot of code to be able to call decode from Python, from Excel, from our internal language at Symmetry. So without reflection, this would be a lot more work. I mean, people do call, for instance, C++ from Python, but it does involve a lot more. In D, also, we have custom testing frameworks. So the most popular packages on Dub are testing frameworks, and the only reason we can write them as a library is because we have access to the code and we can look at it at compile time and determine where the unit test blocks are and call it in a different manner than the one that's given to us by D runtime. And I think in short really is about avoiding boilerplate. So we can avoid writing code that we can get the compiler to write for us. And it's hard to be able to do that without being able to look at the code first. Of course, to interface to other languages, we need to be able to see what the decode is that we're trying to call, what functions exist, what parameters they take, all of those things that I just mentioned. And reflection in D, well, we have a compile time instead of a runtime. We have reflection in Python or Java, but it is at runtime and Go as well. And I think we made the right decision here because you don't need runtime reflection if you have compile time because you can generate one from the other. It isn't completely free, but if you just opt into it, you can use compile time reflection to then carry that information to runtime. I think one of the issues we have with reflection in D is there's no one-stop shop for it. We have SED traits and we have double underscore traits, and we have things that are in one or not the other. The whole idea was that double underscore traits is supposed to be ugly so people would use it, and we'd use it to have things in the standard library that people would then use, but it didn't quite work out that way. The APIs aren't quite consistent either, even just within double underscore traits. Sometimes you get symbols, sometimes you get strings, which you have to mix in or use another trait for that. And it does require metaprogramming to be able to use. So this is the status quo right now. And template metaprogramming is very powerful, and it was discovered by accident in C++. However, it does have its own issues. It has problems. It's not really D, right? It's this parallel language that's inside of D as well. I mean, it is D because it's in the spec and it's implemented, but it's also not regular programming. Instead of functions, we have to use metafunctions, and if you're wondering what that means, then I'll explain on the next slide. Instead of using variables and declaring them with auto or const, we have to use alias and enum, and we need to remember which one is which because they're not interchangeable. And instead of using higher order functions like map, we have to use static map instead, which is basically a higher order metafunction. It is a lot easier to do indeed than C++, but it's still not exactly easy. We have heard multiple people say that templates indeed made them think that they could actually do template metaprogramming because it's so much easier, and it is. And some of the reasons for that is that we have static for each, so we don't have to use recursion to do everything. We can index into variadic templates. Anything could be a template argument, which helps a lot. And built-in arrays and slices really do help with a lot of this as well, because we can just put things into arrays, pass them as a template argument, and things just work. Also, the fact that variadic templates kind of act like they were arrays to begin with the indexing. We've had implementation problems though. Compile times go up, which is common. This is not something that's particular to D. And we've also had symbol omission bugs in which we have linker errors because certain symbols didn't get omitted. There's a reason why the flag -all inst exists in DMD, and that's to omit all templates. So all of these can make working with reflection in D today. A lot harder than maybe it should or could be. And speaking of meta functions, here are two examples. So we start importing SED meta here, so we have access to filtering static map and also alias sequence and what have you. Our first meta function here is large, which is a predicate. It takes a type, it maps a type to a Boolean. So if the size of the type is more than 4, this is true. Otherwise, it's false. And we can use this just like we do regular filter, but it's not regular filter. We have to pass this in as a compile time argument, and then everything else that comes afterwards is what we're filtering on. A lot of the times you won't see, well, most of the times you won't see the rest of the arguments bundled in together like this. They'll be in an alias sequence beforehand, but that's how it works. So the syntax is different, right? This isn't a function. We don't declare it like it's a function. It's a meta function, it's a template. And if I use alias instead of enum here, it's not going to work. It's not going to compile, and the messages aren't going to be that helpful. And that's because its large maps a type to a Boolean. A Boolean is a value, therefore I have to use an enum, and I need to know this. If I do that pragma message, then what the compiler prints out is double within parentheses, because int, of course, is size 4, doesn't pass the predicate, all we have is double left. This works, but it is different and it is weird. The second example is we have a struct here with two functions called foo, so basically they form an overload set, and then we have another meta function called overloads that takes a string as an argument, and then it returns, quote unquote, the overloads that have that name within the struct. Of course, we only have these two functions, but it has to fit in a slide. And then if I static map passing it overloads as the first argument, then whatever comes next, it will map over, and it will return what we get from that. There's only these two functions anyway, so we get a tuple, which is a compile time construct only available with the compiler, with both of the functions in there. If I index into that, I would get an integer back if I indexed into it and passed 0. And if I indexed into it and passed 1, then I'd get the second function. So this is understandable. This is what people do today, but it isn't regular deprogramming. It's this other bizarre parallel universe in which meta functions are what we use. And so to address this, and also based on some ideas that Andre talked about, if I'm not mistaken, in DConf 2019, I started writing this library that I called Mirror, which is an attempt at a better and centralized API. So it is your one-stop shop. This is where you go to actually be able to reflect on the code. The URL is there if you want to check it out. It is, of course, available on Dub. It isn't finished and experimental. I'm still working on it. I'm still trying to figure out what the best APIs actually are. And it does basically 3 things. It provides some extended RTTI support for D, which kind of looks like Java's runtime reflection. And it does compile time reflection in 2 ways. The first one is traditional with metaprogramming and symbols. And the second one, which is the really new thing here, except for the better API for the first one, a CTFE API with values and strings, so just regular values, just structs with strings within them, or other structs with strings. So let's look at each of these in turn. I don't want to spend a lot of time on the better RTTI. I don't do a lot of OOP programming, and so I'm not entirely sure how useful this actually will be. But the idea here is that I can take a value at runtime, and I don't know its type because it's OOP, so it's a subtype of some kind. And you can see here that I'm declaring OBJ as explicitly as abstract, which means I'm type erasing it. So I can't know what the real type of that object is. And that with types class, what it's doing is registering types, in this case, only one type, class, with a capital C, because we need to opt into this, right? We need to say to the compiler, look, at compile time, look at these types I'm going to give you. And given that, now generate some runtime type information for me. And I'm doing the with, so I don't have to type the name of the object that's in there, because RTTI is actually a member function. And then I can get the type of object, and then I can check its fields and say that the fields are of type integer and type string. And as you can see here, it's not replacing the type information we already have in the runtime, it's extending it. So we're using type ID here so that we can transition from compile time to runtime. So give me the runtime type of integer and string. And that's how we can say that these fields are of that type. Now, this is a silly example. We could have checked that the fields were called I and S as well, and a lot of things as well. But the real meat of this talk is talking about the compile time aspect of the library. And so first of all, let's look at the traditional way of doing this with metaprogramming and symbols. It's all based on the module because in the module is the unit of encapsulation. So let's look at modules individually. The way we do that is by using this template called module, and we pass it a string, which is the fully qualified name of a D module. Now, why a string? Well, because otherwise you'd have to import that module to have access to it, and then you could pass the symbol in. But that's more work than just giving it the name, and then the template can import it inside of itself. I am importing the original module here, but that's because this code has been taken from a test. And the reason for that is so I can refer to the functions within the module so that I can actually check that I got what I expect. Because it's a template and not a value, I have to use alias here, and it's not and enum wouldn't work either for obvious reasons. And inside that template, there's several other templates and things are quite complex. And half of this is just setting up the what do I expect to see within that module. And so I've eliminated the rest of the functions here for clarity. And I've only have one here as an example. So I'm expecting to see, well, as the first function anyway, this function called add1, which is public. It's got delinkage, and then there should be other information, but the library is not finished. And of course, this is another template, so everything is a compile time construct, so there's bangs everywhere. Because these aren't values, they're not structs. And because metaprogramming is so weird, I had to use my own custom should equal meta function to be able to compare two alias sequences, because just doing equals doesn't work, and is expressions don't quite work either, and well, things are complicated. But what I'm doing here is actually doing a lot behind the scenes that I have to explain, otherwise it's blink and you'll miss it. Here I'm taking the module, so that template that I declared at the beginning of the first line, and I'm saying dot functions by symbol, and that is giving me the list of the functions by symbol. So I decided to call it this because in the reflection work I've done so far, sometimes you want to iterate over functions by an identifier, and sometimes you want to basically roll out all of the overloads. So in this case, each one of the elements and functions by symbol is an overload set, so you'd have to loop over those again to get each specific overload. And if I said mod.functions by overload instead, they would be flattened and I'd get individual functions. And it really does depend on what the user wants, so we have both options here. And this is doing so much for anyone who's done reflection before. Internally, this is doing traits all members on the module, and then looping over them, and then filtering the ones that are functions, which isn't that trivial because it's also taking care of not generating compiler errors by trying to access symbols within that module that are private. And so it's doing a lot of work, which there's just no way of doing this otherwise today, this simply. You'd have to do the filtering by yourself. You'd have to take care of private functions by yourself. You'd have to think about overloads by yourself because you would get, whether you want to or not, only one per identifier and then have to loop over the overloads. So it's both flatten and not at the same time. So this makes it explicit, and then you get information within it. That function symbol template has the symbol of the function within it and other things that you can use as well. So this is quite nice. But a lot of the focus on the SOC is actually on the other way of doing things, because that is completely new, and that is reflection via CTFE and values. Now, notice here that the only thing that's really compile time is that first line, which has an enum. So obviously, to reflect a compile time, I need to give a string known at compile time. It's a similar thing, a fully qualified name from a module, but this time I get value back. So instead of being alias, it's an enum. And that mod thing there is just a struct. It's nothing weird or templated or anything. It's just a regular struct. It's just a value. It just happens to be a value that we constructed at compile time. And realize that here that in the second line, I'm even using const. I'm not using enum because I don't have to. And I'm getting functions by overload this time. And then I'm just taking the first one because I'm only checking the first one here. I could use regular equality because these are just values. It's just completely regular D values. And functions by overload index 0 is an object of type function, which is a struct. And this struct here has these values that I'm constructing completely normally. So first, what module is it in? The index in the overload set, its identifier, the return type, and then an array of the parameters, which have a type and identifier. And of course, they should also have default values if that were the case. So this is what it looks like, and it's just completely normal programming. And it has strings inside of it because then we can mix things in. And this is how you would use that. I'm not entirely sure if this code is completely useful or not, but I'm lacking the use cases to know. But right now, this is an API that you can play with. We do have to use enum this time for the function because we're going to mix in strings from it. So it won't work if we try to use const because then it becomes a runtime construct. So now add1 is still a value, still the same function object, but we can mix in the strings that are inside of it. The first thing we need to do is import the module the function is in, otherwise we're not going to be able to call it. And then we can mix in the fully qualified name parentheses with the arguments we're going to call it with, and then it actually does return a value. And so this is quite new, and I think it's quite interesting to show. As an example how you can use this in real life, I have tried to boil down to the bare minimum how we can create a Python extension module. So this is a Python module, which is a dynamic library that Python will load at runtime. And what I want to do here is take a D module called D module, and it has functions foo and bar within it. I want to make those available to Python. And to be able to do that, this is basically the bare minimum code I need to write. I need to create the Python module. So in Python, if you say import my module, it will look for my module.py. If it doesn't find that, it will look for my module.so, and then it will open it. And by convention, it will call a function because it needs to know what the entry point is, pyinit underscore name of the module. So this function has to exist with that name. It has to be an externc function, and it has to return a PyObject star. PyObject star is basically Python speak for any value ever. There's a missing semicolon there, but I have created a function to make creating Python modules easier. So that's that create Python module bang. My module is the name of the module as a string, and then foo and bar are the two C functions you see right here. And those functions are going to be what Python calls when somebody tries to call the Python function foo, it calls this C function, so I need to tell it what it is. And the reason why those functions are there is because I need to tell Python what the function pointers are that it needs to call. So basically it's associating a function pointer with a identifier. So foo is this function pointer and bar is this function pointer. But since this is D code, I can just pass the symbols in, and on the other side, we'll get the function pointers. And then both foo and bar are basically identical. The only difference is they're adapted to the D function that they're wrapping. And the first function, foo, the D function, takes one integer argument, and the second one, bar, takes a double and a string. So in both cases, we want to convert the Python arguments to the relative to the D ones we need to call the function with. We get the return as a D value, and then we convert the D value back to Python. For the sake of argument and presentation, let's just assume that these functions exist, and so the conversion functions all exist. The signature of the Python function is like this because self is the module in this case, and args is just the arguments that the person passed into Python. So this is the code we want to write, need to write, compile into an SO so that we can call it from Python. But we don't actually want to write this, right? Because well, if we have 100 functions in the module, we want to have the compiler generate this code for us, and we can. Using reflection, we can go look at D module, see that the functions are called foo and bar, see that there's only two of them, see what the parameters are, and generate this code for us. So what does that look like? So this is a init function, and this is just a regular function. There's nothing, there's no template arguments here, there's nothing. Completely normal D function that returns a string. It takes in the name of the module that we're going to create, the Python module, and that module structure it takes as a second parameter is something from mirror. It's just a struct with the information in the, of the module inside of it. And you can see that we're returning a quoted string that looks like that function. So I'll go back to show it. This function here, pyinit my module. We're constructing it here with appending the name of the module after pyinit underscore. And then the only thing this function really needs to know is what the names of the functions are, because we're going to generate the functions afterwards. So it does that by looking at the module, going functions by symbol. Why by symbol? Because I want people to be able to call all of the overloads from Python. Since Python's dynamic, they can pass anything they want to those functions in Python land. And then we should somehow disambiguate afterwards which overload they mean, by depending on the types of the values they pass in. Map it to identifier, and then join it with a comma, because literally all we're doing here is passing the names of those functions. And there you go. We generate that function. So go back again. That's that first function there. What we need to do now is generate foo and bar, so the two other ones. What does that look like? Similar function here, returns a string. It's taking an array of overload sets. Again, overload set is a type that comes from mirror. It does what it says in the tin. There's a bunch of functions there that form an overload set, and then you can reflect on them. Here, I just have a string return, and then I'm appending to it. I'm not going to deal with overloads right now because I don't feel like it. So we loop over the overload set for each one. We take the first one because we don't want to care about any other possible overloads. And then we append a function definition for that. So we're passing that fun object, which is a function value, into a different function that I'm not going to show that creates a string for each one of those functions. So this is just a looping over each D function and generating the appropriate code that we're going to append later. The previous function used ranges and map, and this one is just using a regular for each. It's just regular D code. You can use whatever you're most comfortable with. Now, what are the advantages of mixin-based program? First of all, compile times. I don't have any numbers to show you, but it's actually astounding how fast everything just was. It was just ready, and it was amazing. And I'm just not used to it because I'm used to reflecting at things taking quite a while. And this is with the regular CTFE end. There's nothing special here. The other thing to realize and that's advantageous here is it's just regular programming. You can pick whether you want to do imperative or OOP or functional. Maybe you want to have a hierarchy of classes for generating these strings. Maybe that's what works best. You could do that as just regular code. It just happens to be run at compile time. And even though these templates are easy, well, this is a lot easier. Anybody can do this. However, not everything is nice. At one point, I thought it was so easy, it's hard because I'm so used to templates and static for each that my mind was confused that I'm passing in things at runtime. It's not runtime because I'm calling it compile time, but it looks like it. And so I think this is just a question of getting used to it. The other problem I had is there's no prior art. There's no best practices. So I'm basically learning as I go along. For instance, do I loop in this generated code and then enroll everything, or do I insert loops into the generated code? I'm not sure yet. I went with enrolled code because it just looked easier. In terms of organizing code, I'm still not sure how to do it. So should we have mixins within mixins? Should I return a string that inside of it mixes things in? Is that going to complicate things? I'm not sure. Is it going to slow down compile time? Also not sure. So there's no guide here. We're all just going to have to learn together how to do this. We'll always have to import modules, of course, because if you're using templates and you have a type, well, you got that somehow. But I can always pass that into another template, and I don't need to do anything. It's a type. It's, I can reflect on it. When you're using strings, you have to import the module the type comes from first. Always. Doesn't matter how many times you've done it. That's a very minor issue. Now, one of the things I started thinking about is that the generated strings will have bugs. They're functions. It's code. Functions are assembling these strings. We will write bugs, which means we're going to have to look at the generated code. And if the generated code is very large, I'm not sure how we're going to do that. There's no tools to do this. In fact, I mean, the best I can do that I know of is pragma message. I think I won't even have syntax highlighting. I'll have to copy, paste it somewhere else to look at it and figure out what's going on. As you saw before, I was using format, and the lack of string interpolation right now makes this harder than it should be. I think string interpolation was basically made for this because it's long form code and it's a lot easier to escape from the string as you go along than otherwise. I think that for one-liners, string interpolation isn't even remotely interesting, but I think here, especially with Q-coded strings, it really shines, or would shine if we had it. I still don't know how to compartmentalize the code. For instance, for each one of the D functions, I needed to synthesize basically out the ether a C function with a particular, I'll go back to it, signature. So these two, foo and bar, I had to basically create functions as I went along for each particular D function. And the way we're doing it here is by appending more strings and more strings. And where do I put them? Where do I generate them? I'm just appending to, an empty string, and it's hard. It's not very neat. It's not organized. Whereas if I have templates, then I can do something like this. If I need to generate a string out of nothing, and this is actually taken from Átila, also a package on Dub. This is a template called Python function, and it has a template argument, which is an alias argument because it's a function symbol, and it's a D function symbol. And inside of this template, it has the implementation that we saw before with self and args and returning a Py object. And implementation is it's delegated to something else, but basically call this D-like function, make sure that it doesn't throw, so basically catch the D exception, generate a Python exception if you have to, and it forwards. Now, the beauty about this is it's a template, so it doesn't really exist until I instantiate it with something. But once I do, that function exists. So by virtue of just taking the address of that internal function, I make it exist, and then the compiler emits it to object code, which is a very different thing from what we're seeing before, in which I have to create them on demand, as it were. And here, it just kind of pops out the ether. Basically, all functions that we ever need exist. All we have to do is refer to them, and then they'll be available. And I want something like that for the strings, but I'm not sure how to do it yet. To conclude, I think the built-in batteries that we have for reflection could use an upgrade. For instance, there's no easy way right now to say, give me all the functions in the module using the standard library and the language itself. This is why Mirror is here. Template metaprogramming is harder and weirder than regular programming, no matter how easier we've made it compared to our forebears. But also the generate strings isn't a panacea, and I think that we need to solve some of these practical issues going forward and even figure out what the best practices are. And here, definitely, I would like to have ideas and experiences, if possible, from the community. And with that, I am open to questions. Thank you.